Well, thank you for that nice introduction, and thank you for the invitation to speak here today. I should also point out, not being an academic, I'm probably not a professor, or actually not a professor, but thank you anyway. Um, I mean, we've had a really nice first two talks in this session today, and I'm going to take a slightly different tack and talk a little bit about how we analyze data, and more specifically, how we do the initial analysis of data sets in I guess a cheminformatics and a computational chemistry setting. And so, as you can see from the title, this talk is going to be about exploratory data analysis. And it's something we all do, either explicitly or implicitly. And I think there's a number of aspects when working with chemical data that makes it worthwhile digging into this. Many people would call this a boring topic, but doing it properly leads to much better analytics down the road. So we first start out with what is the goal of exploratory data analysis, or EDA. And fundamentally, it's a way to ask questions. You have some data, which could come from experiments or other analyses. And you probably start out the analysis by having some questions in mind. So for example, if you're building a QSAR model, your question is, can we predict this endpoint? Maybe it's an IC50. But EDA aims to sort of raise other questions that you may not have thought of initially. So I'm going to come back to the QSAR example a little later, but if you go in the literature, EDA is a formalized topic in the field of statistics. And I've highlighted two links here, which go into a more formal and technical discussion of what EDA is. And if you look at the first point in this link, which is taken from the tidy universe, you'll see that one of its goals is to generate questions about your data. And I think this is probably the most valuable aspect of doing EDA systematically and properly upfront, because you come in with a certain idea of what you want, and you may not be aware of the other things that are possible given the type of data that you have. And while I sort of phrase EDA as something that we do at the beginning, I actually think, and this is what the diagram shows, it's not one thing that you do at the beginning of your analysis. You will come back to EDA throughout your analysis workflow. And the whole point is that as you ask questions, you find answers to them, and then you have more data to explore, which drives more questions. And there are a variety of ways to do this. The Wikipedia link shown at the bottom provides links to a lot of academic literature that addresses aspects of EDA. So one of the reasons that I chose this topic today is that EDA is domain specific. So if we view this from a statistical point of view, then you ask questions such as, is this data normally distributed? Is there some sort of bias in the data, etc., that is applicable to whatever data you have, whether you're doing cheminformatics or comp chem or bioinformatics and so on. But the fact that we are operating on chemical data implies that there are questions that we can ask in an EDA setting that is specific to chemical data. So that brings us to the idea of EDA strategies. And most of the literature has settled on three broad characteristics of what one might do when doing exploratory data analysis. So the first thing shown on the top left is looking at distributions of your data. And I'm sure that everybody who's built QSAR models has plotted the distribution, looking for normality. And if it's not normal, you try and see if you can transform the distribution into something that is normal, and so on. And so looking at distributions really gives you an idea of how that data might have been generated. Do you have clusters in the data, and so on and so forth. The second strategy is to look at correlations. And so you have data, you might have descriptors, or you might have multiple observations. And the first thing that you might look at is, do we see any correlations? If plotting a correlation plot gives you a random scatter, then you probably have problems ahead of trying to develop any sort of model of that data. Whereas if you see a perfect correlation, that again might raise flags because the data might look too good. But just plotting various types of, was there a question? Okay. So just looking at correlations between different things can sort of raise a lot of aspects around your data, or a lot of features of your data that I mean, you might want to dig into and sort of have questions about. Okay, the third strategy, and I think this is the one that probably we're all familiar with, especially in the field of cheminformatics, is dimension reduction, or I should say dimension transformation. So we usually start off with data sets where we have, say, a number of observations, but it's very easy to describe them in many ways. So you're probably familiar with tools like Dragon, which calculates 3,000 or 4,000 now descriptors for a single molecule. So you're talking about a molecule embedded in a 5,000 dimensional space. And we know that many of those dimensions are correlated. Many of those dimensions don't have information in them. And most importantly, you can't look at a 5,000 dimensional space. And so there are many ways that we could try to reduce a high dimensional space to a lower dimensional space that is, one, more informative, but secondly, also something that is more amenable to us to explore visually or interactively. And so there's a whole slew of methodologies to do dimension reduction. And so the last sort of strategy that is on the lower right corner, and I think is probably the most relevant to us as we work with chemical data, is representations. And this is most familiar in chemistry because we know that we can represent a molecule in many different ways. So for example, benzene could be a simple formula, C6H6. It could be the 2D connectivity diagram. It could be a 3D structure, or, and I haven't shown that here, a series of 3D structures, also known as conformations. And so when you're trying to ask questions of what type of analysis should I do, or why does the data look like this, in some cases, and I would say actually in many cases of chemistry, exploring different representations can give you insight that really helps you either answer the problem that you're looking at or raise other questions. And I think this last point is extremely important, not just for things like predictive modeling or any sort of machine learning on AI, but even if you are doing sort of application modeling, you're looking at a structure-based design problem. Considering the representation, in which case maybe shape is more relevant than a stick and ball model, can both, as I said, help answer your question, but also raise other questions that you might want to follow. Okay. So I think it's also important to understand the role that models play in EDA. Especially in cheminformatics, a lot of us are building models to predict something. And in many cases, I think we see the model as the end result of our analytic workflow. You then have a model that you can then use to make predictions, which go into the lab, etc. But the sort of computational analytic workflow ends as a model. But it's also true that exploratory data analysis can make use of models. And I think the distinction is really one of complexity. In general, when you're in the EDA end of the spectrum, as shown here, you're really looking into the data, and you don't want to impose too many assumptions or biases that you might have if you decide to start modeling right up front. In many cases, you have to actually look at the data before you can even decide what model you should use. And so as your sort of project progresses, as you sort of start exploring your data, the sort of EDA end of it will start using some form of model whose complexity increases. And at one point, you've understood your data, you've understood the characteristics of your data, and now you're in a position to bring in formal modeling. So now you can ask things like feature selection, model validation, and so on. And so the other difference that we have to keep in mind is that EDA is, you're trying to understand your data set. And so by definition, you're looking at all of your data set. So a lot of the principles of good predictive modeling, such as test train splits, various forms of validation, just don't make sense when you're at the EDA end of the spectrum. And so even though you might want to use, say, for example, a linear model with interaction terms to just understand whether certain descriptors interact with each other, you're going to build that model using all the data. You won't have a test train split to validate the model. And that's fine, because your goal is to understand, is there an interaction? I mean, you're going to validate those assumptions later on if you decide to go down that route. But all you're asking here is there an interaction between terms? And therefore, yes, use all the data and don't worry about a train test split. But once you sort of progress through your EDA and end up on the right hand of this spectrum, when you're formally modeling, then yes, you now have to or should follow best practice in machine learning and predictive modeling, where you will have train test splits, you will have specific questions about validation and so on. Okay, so having laid the sort of groundwork a little bit for predictive modeling, EDA, you might ask, where does it get applied? And I'd argue that it's everywhere. As I said before, many of us don't really formally call this EDA, but you are looking at distributions, you are looking at correlations. So you're either doing it explicitly or you're doing it implicitly. And I want to go through a few examples of where EDA comes up, but I do want to sort of start with maybe a trivial example. For those of you who have Netflix or Amazon or any other movie or music streaming account, how do those accounts decide what movie to stream or what movie or song to present or recommend to you when you log into your account? And so here the question that you come in with is, what movie should be recommended next? And as you develop these recommendation systems, you want to explore the data using EDA. And so simple things like, what do most people want to watch? Do they want to watch a movie or do they want to watch a TV show? This data, which is actually taken from a Netflix blog post, suggests that people mainly want to watch movies. This will affect how you describe your objects, which are essentially shows. In which month is content added most? That could influence how you make recommendations based on what is coming in that month or upcoming in the next month, or you may want to pool the data. Similarly, what type of content gets added over the years? It looks like international movies are the most frequently added type of content. And therefore, you may decide that you want to choose a modeling approach that better represents less frequent topics here. And so the point of this is that even as something as sort of ordinary or taken for granted as movie recommendations, really depends on understanding the data that is underlying those recommender systems. So to something that's more maybe closer to our field, EDA is critical to many scientific tasks. So I'm going to discuss three areas where this comes up. So high throughput screening is an area that I've worked on for many years. And the scenario that comes up here is that you're working with a project team. They've run a large primary screen. You have, let's say, 500,000 data points of compounds measured in single point. You have their measured activities, maybe percentage inhibition. Maybe there is some secondary data or secondary assay that was run for a subset of them. Or you have access to a resource like Campbell, which contains data on other assays, but that are related to your data set. So you have access to a large amount of data from a variety of sources. Before trying to, say, select a active from your HTS, which is the sort of primary question in that scenario, you want to explore the data. You want to maybe look at enriched chemotypes or nuisance compounds. Is there a particular scaffold that seems to always have a high activity? Or are we seeing, say, fluorescent compounds always show up as actives? This immediately suggests, okay, before I try and select an active or a validated hit, maybe we need to see what type of biases, what type of assay was run that might be sensitive to certain chemotypes and therefore appear as false positives. That's sort of looking at the individual compounds. But then you also want to look at plates. Do plates show patterns on them? Are we seeing batch effects? Or maybe the dispensing of compounds on plates is non-random, and so you see correlated patterns on the plate and so on. This then leads to the question, can we fix those patterns or take those into account when we make selections so we don't get biases or over-enrichment in one particular type of compound? And finally, I think it's quite common also to use predictive models in HTS triage. And so you'd want to look at various distributions. You want to look at whether certain clusters of compounds are distributed differently in various phys-chem property spaces, all of which will influence how you subsequently model the data and then finally make selections for further study. The next area is predictive models. And again, it's a similar situation. Either we are generating data or we receive data from collaborators. We're asked, okay, can you predict this, I don't know, let's say IC50? Hopefully we don't just throw it into R or Stata or something and just build a model. We have to look at the data and see, is it, first of all, modelable? And if so, what type of model should we address? So again, simple things you're going to look at is you'll compute various descriptors. You want to look at correlations of the features, get rid of correlated features. Obviously, you want to look at the distribution of Y. Is it normally distributed? If not, you're going to have to transform it. If that doesn't work, you may have to go to a method that doesn't make assumptions about normality and so on. Similarly, you may want to look at interactions in your data, which again, if you start off using linear models to test for interactions, that might suggest you need to stick with linear models down the road, or else identify a nonlinear method that can also take interactions into account. And it is certainly possible that the outcome of all this is that, no, this model or data is not modelable. And this then goes back, sort of starts another conversation with the experimentalists in how did you generate that data? Maybe there's a better way to generate that data that will lead to better model or more modelable data and so on. Finally, another area that I've worked in that sort of also requires us to do EDA before really doing any formal analysis is image analysis. And in this case, let's say you have a high throughput phenotypic screen, you've got multiple images of each well in that screen. You then want to apply some image analysis routine to, say, capture morphology of cells and so on, compute features, and then make calls on actives or inactives. In this case, it's, again, similar to what we might do in HTS. We want to, as well as predictive models, you want to look at correlations between the various readouts, because in many phenotypic screens, you do use multiplexed readouts. You want to look at the channel statistics in individual channels. Maybe some are due to sort of experimental setup, are highly saturated, and therefore there's no useful signal there. Other channels may be more normally distributed and so on. Obviously, you want to look at plate patterns, and then you want to look at cross correlations, as I mentioned already, cross correlations. Once you have an idea of that, in many cases, you may need to go back and tweak the imaging setup so you get better images. In some cases, we can use modern deep learning methods to denoise signals or remove batch effects and so on. And after doing all that, you then finally have clean data that you understand that you can then go to analyze. Okay. One of the points I also wanted to raise in this talk is that sometimes a lot of the work that I do in this area is in an industrial setting, and which has some constraints and some requirements that might differ from those of us not operating in an industrial setting. One of the sort of biggest constraints is speed. But before that, I think the stuff that I've listed here applies sort of uniformly across anybody or any environment that has to do EDA. So data can be big or small. You might have a data set of 50 compounds or 50 observations, or you might have data sets of 500,000 or 1 million compounds. Data can be outdated or missing. This is especially so when we work with data from our historical archives. For example, data might have been run on an old version of an assay, which is sensitive to, say, nuisance compounds or various artifacts, but the latest version of the assay is not. So the question is, can you merge those types of data? Usually we'll work with lots of different data types, sort of small molecule, maybe single point readout is one of them. In many cases, we have proteomics data, transcriptomics data, and so on. And so one of the sort of important constraints is working out what is the relevant data type to answer the question, and then rapidly working out a way to integrate that data. And then the nature of integration is going to be driven by the types of questions we want to ask. If your only question is just what is the most active compound that I can then do lead optimization on, all you need to do is look at your high throughput primary screen plus the secondary orthogonal screens and so on. But if your question really is, we're looking for a compound that we can do lead opt on, but is very specific to these pathways, in that case, you probably want to start integrating your small molecule assay data along with some transcriptomic data to enable chemogenomic type of analyses where you want to identify enriched pathways and so on. And I guess within the industrial setting, some data types are regulated. This can represent challenges in accessing that data and sort of accessing it in a form that enables useful modeling. And as I mentioned, the timelines can be very tight. We may need to operate in days. If we're lucky, it might be a few weeks. And so these constraints lead to some implications. If you want to do the integrations that I described previously, you need infrastructure to be in place. You want databases to be available. You want your workflows to be implemented, your code to be reusable, and you need compute power to run these so that you don't have to do everything from scratch. But coming back to the point of EDA, EDA needs to be efficient, both in terms of execution as well as communication. So not only do you need to do these steps reasonably fast and correctly and rigorously, those output of those steps then have to be communicated to the project team. And as I'm sure everybody knows, pulling up a PowerPoint with a big dense table is not a good way to make your message go through. If you want to say that the data cannot be modeled, you have to present it efficiently. And if you say that I can model this and this is what I found, you also need to say that efficiently. Okay, so I'm going to switch gear a little bit and sort of move into the topic of visualization and communication. And the reason I think this connects to EDA is because a lot of EDA is looking at the data in some form. Usually you will have to apply methods to transform the data to enable that visualization. But fundamentally, when you look at distributions, you are looking at a density plot. If you're looking at correlations, you're looking at a scatter plot. And if you have high dimensional data, you need to somehow model that or transform that so you can make these types of 2D or 3D plots, or maybe a series of 3D plots and so on. And so I think this, for those of you who may be familiar with linguistics, there is a sort of a theorem, or, well, not really a theorem, but a principle that was stated originally as the structure of a language determines or greatly influences the modes of thought and behavior that are characteristic of the culture in which it is spoken. Now, this is called the strong form of this hypothesis, but it is now been sort of softened and generally recognized that the structure of the language you speak influences how you think, and therefore the things that you can do. And sort of related to that, or inspired by that statement, there is this quote by Bridget Cogley, who works at Tableau, which is a well-known visualization environment, which essentially says that the limits of the tool shapes my reality. And I think this is a very fundamental observation, but also a very practical observation. You can look at the data and draw conclusions of the data based on how you work with that data. If you don't have the ability to generate and look at scatter plots, you can't really say anything about correlations. Okay, if you don't have a way to show 3D plots, you can take 2D slices of your data and have lots of 2D plots. But it's not guaranteed that you can really understand the shape of the data in 3D easily if you don't have that ability. And so in many ways, what you see or what you can conclude from your data is very much driven by the tools and workflows that you have that let you manipulate that data. And so this is my favorite example of how sort of data representation underlies so many things we can or cannot do. So you can see all these plots. This data set is called the Datasaurus dozen. And I think you will see 11 plots here. And they look quite different. Yet, if you compute these various summary statistics, the mean along the x, the mean along the y, correlation, etc., they all have the exact same values. And so if all you did was compute averages, you would conclude that all these data sets are the same and therefore, I mean, not dig into it more. That would be a mistake. And the reason this is called the Datasaurus dozen is that this plot up on the top right also has those same values of x, y, means and standard deviations and correlations between x, y. And so I think, if nothing else, this figure sort of should guarantee that you always plot your data in different ways to look at the structure of it. But again, going into sort of coming back to the topic of communication, as I mentioned, you want to be efficient in terms of how you communicate the data. Now, efficient means it also has to be rigorous and truthful. And it's not difficult to present things in a manner that is, I would say, unfaithful to the actual sort of data or situation. And in some cases can just be outright false. So for example, this box plot here is interesting. It shows that there are some differences between the groups and it gives you an idea about the size of the groups. For example, this, I guess this, well, it doesn't really tell you what the size of the groups. Okay, but it would suggest that this green box here is sufficiently different from these other twos. Even this blue box is also different from this purple box. But box plots and bins hide data. If you actually do the box plot with jitter, now it tells a somewhat different story. Yes, the green box has a median value that is statistically significantly different from all the rest. But if you look at the amount of data that goes into that category, it's far, far less than any of the others. And so how much confidence do you have that that is really different, even though the statistic says it is different? Similarly, you can see that in the purple and the blue boxes, the distribution of the data differs. Even though they have lots of data points, the blue category or category B has a much tighter spread of data, whereas category A has a much wider spread of the data. And knowing this lets you think about the problem slightly differently. And so now you have communicated sort of the differences in the data, but he's also given the viewer an idea of how much data are we actually talking about that underlies these differences. But that's a slightly ugly data set, even though it does suggest that there is some clustering in category B, right? It looks to be a little bit above and below the median. So if you go to violin plots, that again gives you a better idea of the differences between the groups, but also an idea about the distribution of the data within that groups. And now the clustered nature of group B is made much more clearer. And we still have an informative or a piece of information that indicates the size of each category. And so the fact that we see two clusters for category B with 1,000 data points gives us a little more confidence that that is actually a true distribution or a true sort of separation of that data set. And if someone could just let me know when I'm about to, when I have 10 minutes left, that would be great. So another example that I always like to bring out is how binning actually makes things or gives you a false view of the data. This is a figure taken from a paper by Montanari and Kenny, where it looks like if you look at these data plots, there's an increasing improvement in the R squared or the R out here. And you can see that as you go further and further to the right, your lines are coming, sort of points are becoming more aligned. But the data points here are actually averages or aggregated data. If you look at the actual data, this is what it looks like now. And then when you look at or compute your statistics on all the data, you now see there actually isn't a difference between the three cases out here. And it's easy for us to fool ourselves or make our jobs easier by doing aggregation. We think it might be a cleaner way to model the data, but as you can see, it leads to quite misleading outcomes. So the question then is, it's fine to do all sort of look at these various things in an exploratory setting because you're the analyst, you're going to look at a lot of plots, run scripts and code and sort of explore the data. But at one point, you want to be able to transmit your findings to your collaborators or your colleagues. And those collaborators could be at a project team meeting where you can still put up a PowerPoint and walk through things. But in many cases, you need to deploy these analyses or your observations to a production setting. So at Vertex, a lot of our time is spent in developing predictive models and characterizing the data underlying them and the predictions themselves, but then deploying it to chemists who will operate or use those observations and data on a day-to-day basis without having to come to us. And in this case, a plot like this, it turns out, is quite useful when displaying predictions from a model. And so what this shows is you have a chemist drew in a query compound, got a prediction for it, shown by the blue dot at the top line. And our models are able to predict a confidence interval for that prediction. That's shown as the dashed line here. If you had nothing else, this is still, I guess, moderately useful. It says that this is your prediction and this is how confident we are about that prediction. But we can get more, it can become more useful if we then show the predictions for the nearest neighbors of that query compound. And so we pull out 4 nearest neighbors, and for each of them, we show the predicted value and the confidence interval. And as you know, by the similarity principle, if those nearest neighbors are all similar to the query molecule, we would expect similar predictions of them. When we don't see similar predictions or we see greatly different predictions, then that suggests, okay, maybe we're operating around an activity cliff, and then, okay, we should take appropriate action. So that's one level of information that we can provide to contextualize the results of the analysis. But you can go one level more and provide some confidence in the model itself. And for nearest neighbors, because these molecules have been tested before, we can show the actual assay value and compute a standard deviation or a sort of measure of variance of the assay itself and show that in relation to the prediction. And you can see here that in most cases, the prediction is pretty close to the measured assay value. And so now we've been able to add a piece of information that says the model is actually pretty decent. And so if the model says your query is going to be predicted at this, you probably should believe it. So this is an example of efficient communication. We've sort of layered in multiple aspects of the prediction confidence, and the overall model confidence into one easily digestible figure. But at the same time, you want to be able to go down, drill down, and provide access to the data to let people get answers for themselves. So for example, if you're running high throughput screens, looking at plate statistics is very important to judge the performance of a screen, and if the statistics don't look good, take action. So we have a tool that displays, as you can see here, average statistics across all plates, which is a good first step because you're not overwhelming the user. You give them an overall view that, okay, it seems to be running fine. But again, aggregates, as you've seen, hide individual details. And so we want a way for the user to get down to the individual plates. And so again, rather than having a table with 600 or 1,000 rows, let's look at distribution plots or box plots of a given statistic. So now you can see that there is some difference in the performance of the assay, especially in the beginning, but over time, the assay turned out to sort of tighten up. And one could even then dig down into each batch and look at individual Z primes for individual plates and so on. And finally, I guess it's important, especially when working on drug discovery projects, to be able to access all the relevant data. And this can be a huge amount of data on large projects. And this is a screenshot from one of our workhorse tools called ASAP. that is an interface to present multiple data columns as well as multiple types of data. So activities, selectivities, properties, and so on. Given I have 2 minutes left, I'm going to run through a little bit. I just want to highlight, given that we are speaking in a cheminformatics setting, that exploring representations is very important. And this was a really nice project that I worked on at the NIH, where we were doing drug combination testing, where you tested N drugs against M drugs. And in this particular experiment, we tested 50 compounds against 50 compounds to find the pairs that would be most synergistic in their antimalarial activity. And the question that we were asking is, can you find the set of compounds whose combinations are the most synergistic? And if you have this type of table, it turns out that it's non-trivial to identify the smallest set of compounds that will be, or smallest set of combinations that are the most synergistic. But if you were to transform that table into a graph where each node is a drug and they're connected by an edge, if they're tested together, you get a graph that looks like this. Everything is connected to everything. But it turns out that there is a method called the minimum spanning tree. And if you compute the minimum spanning tree, it will identify the set of combinations that optimizes or minimizes the edge weights. And if your edge weights are the synergy score, you will have at one go identified the set of combinations that are the most synergistic. So this is a really nice example of, if you can find the right representation, the answer to your problem can become much, much easier. In the interest of time, I will skip programming. I think this is an important thing because it goes back to that point of the types of tools that you have sort of affects how you view your data and whether it makes your life easier or not. I will make a plug for R, because I think when you're doing a lot of EDA, R is probably the most flexible environment for slicing and dicing your data. But having said that, what you can do in R, you can do in any other language. And so you should use what's comfortable for you. And so I make this point here. And I just also want to point out that in many cases, exploratory data analysis can actually become a product on its own right. And an example here is where we showed did an exploratory analysis of assay cycle times. How long does it take for a molecule to be submitted to an assay queue and then get a result? And it was basically plotting distributions of elapsed time. But it turns out that this was useful in highlighting bottlenecks in our assay workflows that was very useful to project teams. And so what was a Jupyter notebook then became an actual web app that now project teams can go and look at. And I do want to make a plug. I used to teach informatics and programming a long time ago. And now that I lead a computational group, I think software development and programming is extremely useful when you're doing EDA, because you're writing code to explore your data. You don't have to be a rockstar programmer, but you should be efficient and you should follow best practices so that once you've done your EDA, some parts of that can then go into your formal computational workflow. And as I point out here, hacky code is fine when you're doing EDA. If it becomes production, you want to put in the time to strengthen it. And finally, I will make the plug that in an EDA setting, having access to all the data that you have access to is worth it. It takes effort, but once you have data sets such as open targets or Pharos, as well as your own internal data set, it allows you to reap many benefits. You have guidance because now you have context from external data sets. You're able to summarize your data better. And one of my favorite topics is that it enables or increases the probability that you're going to find something of interest that you may not have thought for before. And so with that, I'd like to thank my colleagues, Stephen Capuzzi and Adam Bleckert, who helped with this presentation, and thank you for your attention.